This video will walk you through solving a linear program problem graphically while giving you a strong conceptual understanding of how these solutions logically work. Here, we have the summary of the model we previously created. Over the next several slides, we will plot the constraints and then apply the objective function to determine its optimal maximum value. Let's start with the butter constraint, which we get by plugging 0 into each variable and connecting the points into a line. And because the constraint is less than or equal to, it means our feasible area is everything below this line. This tells us that with the 6 sticks of butter we have, if you make 1 sugar cookie, you will only be able to make 2 chocolate chip cookies. And if you make 2 sugar cookies, you will have enough to make 1 chocolate chip cookie. However, if you make 1 sugar cookie and 1 chocolate chip cookie, then you will have leftover butter. Let's look at our next constraint. Next, let's look at our sugar constraint. 0 plus 2xs equals 5, which means that xs equals 2.5. And then we do xc plus 2 times 0 equals 5, which gives us a chocolate chip cookie of 5. We want to plot the 5 here, and then plot the xs here, and then draw the line. What's important for us to notice here is that when we add the constraint, it changed the size and shape of the feasible region. Now take a moment and think about why this region shrunk when we added the sugar constraint. Now that you know how to plot the constraints, let's look at what the graph will look like when we plot all of them. Here, I want you to take notice of a couple of things. First, notice how by adding the chocolate chip constraint, it further shrunk our feasible solution space. Earlier, I asked you to ponder why this area might shrink when we added constraints. Well, this feasible space is the area that satisfies all of our constraints, meaning that any combination of chocolate chip cookies and sugar cookies that follow our objective function and falls within this space will satisfy all of our constraints. I hope this hint helps you understand why adding constraints might affect the feasible solution space. Now notice how the flour and egg constraints did not have any impact on the feasible space. These constraints are considered redundant because they do not impact the feasible area. Setting the objective function to 0, we can follow the same steps as before and get the objective function line. However, unlike the constraints, this is a function that does not have a limit. That means that the objective function line can lie anywhere on the graph. Let's now take a look at features that are common to objective functions. First of all, the objective function describes the relationship between our decision variables, which we are trying to max. Secondly, because the objective function describes a line with the same slope, regardless of where we plot these lines, they will always be parallel to each other. As you can see here, we have plotted several objective functions at different values. So for example, if z equals 30, we are saying that 30xc plus 20xc equals 30, which gives us an intercept at 1 and 1.5. Thirdly, the further from the origin we go, the larger the function will be. Therefore, because we are looking to maximize our profits, we want our line to be as far away from the origin as possible. And the opposite is true if we're attempting to minimize our objective. And finally, where we eventually stop the line will always be at one of the corner points of the feasible region. More on this on the next slide. Alright, so let's add these corner points. In this case, we have 5 constraint intersection points that make up our feasible solution space. And now, all we need to do is find the furthest point that our objective function would land on. And here's our solution. So in order to maximize our objective function, we would need to make 2 batches of chocolate chip cookies and 1 batch of sugar cookies. And if we plug these figures into our function, we find out that we could potentially make $80. Now that we have a visual understanding of linear programming, in the next video, we'll take a look at solving it algebraically.